quantum mechanical model. The difference between orbital and orbit. Orbital is a three-dimensional region or space in an atom which there is a high probability of finding the electron. Different from orbit, orbit contains a pathway for an electron to travel around nucleus in an atom. This is the example of orbit. Fixed pathway. This is example of orbital. Three-dimensional region, no fixed path. The distance, variable distance from the nucleus. The orbital distance is variable, but orbit has fixed distance from the nucleus. We know that n equal to 1 is closer to the nucleus, n equal to 2 is further, n equal to 3 is further, and for distance variable from the nucleus in orbital. Path, no path, varied shape of region. For orbit, circular or elliptical path. Quantum number. It is used to determine the location of the electrons in an atom. So we use the quantum number to identify the location of electron. Quantum number can be divided into four. Principal quantum number with the symbol n, angular momentum quantum number with the symbol L, magnetic quantum number, symbol M, and electron spin quantum number with the symbol S. Principal quantum number indicates the energy level and relative size of orbital. So n, principal quantum number, shows the size of orbital and the energy level of the orbital. So when the higher the value of n, the bigger the size of the orbital. Angular momentum quantum number indicates the shape of the orbital, while magnetic quantum number indicates the orientation of orbital in the space around the nucleus. Difference between L and M. L indicates the shape, but M indicates the orientation. It depends on the axis, x-axis, y-axis, or z-axis. You'll see in the next slide what does it means by orientation of orbital. Finally, electron spin quantum number represent the spinning motion of the electron in its own axis, whether it's clockwise or anti-clockwise. Principal quantum number, the energy level, n with symbol n, it must be positive integer, 1, 2, 3, and so on till infinity. It must be integer whole number. It indicates the energy level and the size of the orbital. When the value of n is greater, the energy level will be greater, the average distance of electron or of the orbital from the nucleus is greater. So this is smaller principal quantum number. This is larger principal quantum number. It shows the energy level and the size. The bigger the n, the bigger the energy level, the bigger the size, the further the distance of the orbital from the nucleus. Angular momentum quantum number, symbol L, also called azimuthal subsidiary orbital quantum number. The value of L is an integer from 0 to n minus 1. So it cannot be negative, it must be 0 to n minus 1. It indicates the shape. Angular momentum quantum number shows the shape of the orbital. If the value of L is 0, the name of the orbital or the shape of orbital is S. If the value of L is equal to 1, the name of the orbital is p orbital. If the value of L is 2, the name of the orbital is d orbital. If it's 3, the name of orbital is f orbital, and so on. This is the shape when L is equal to 0. This is s orbital, sphere, and this is the shape of the orbital when the value of L is equal to 1. It is dumbbell, p orbital, dumbbell shape. When the value of L is equal to 2, this is the shape of d orbital. It's clover leaf shape. D orbital has two shapes. You'll see on the next slide. L is an integer from 0 to n minus 1. If our n is equal to 1, our L equal to 0 to n minus 1. So our n is 1, 1 minus 1 is 0. So our L is 0 only if n equal to 1. If our n is equal to 2, L equal to 0 because 0 to n minus 1. L must be start from 0 and our n is equal to 2, so 2 minus 1 is 1. L equals 0 and 1 if n equal to 2. If n equal to 3, L must be 0, 1 and 2. From 0 to n minus 1, our n is 3, so 3 minus 1, 2. So from 0 to 2, 0, 1, 2. If n equal to 3, we have 3 values of L, 0, 1, 2. This is our shell N. The subshell L, value of L is the subshell. The name of the subshell combine N and L. If you want to name the subshell, you must combine the N and the L. Our N is 1, the L is 0. We know that 0 is S orbital. From this, 0 S, 1p, 2d. So if the n equal to 1, L equal to 0, our subshell is 1s. This is the combination of n and L. If our n equal to 2, we have the value of L, 0 and 1. So the name of the subshell, combination of n and L, 2s. 0, L means s orbital, so 2s. This is the name of the subshell, 2s subshell. And 2p. L equal to 1 is p orbital, so the name of the subshell is 2p. Magnetic quantum number. The allowed value for m is integer from negative L till 0 till positive L. Magnetic quantum number indicates the orientation of orbital in the space around the nucleus. The number of m indicates the number of orbitals in a subshell. If our L is 0, m equal to 0. So the value of m depends on the value of L. If our L is 0, m negative 0, there's no negative 0 or 0 and positive 0. So you only have m equal to 0. If L equal to 0 means it is s orbital. L equals 0 means s orbital. M equals 0. For m value, we don't look at the value. We look at how many of m will be produced. So m equal to 0, only one value of m, which is 0. So you only have one value of m. One value of m means one orientation of s orbital. So this is our s orbital. This is the only orientation for L equal 0 for s orbital, this is the only orientation that exists for s orbital. Next example, if our L is equal to 1, and we know that M is equal negative L to 0 to positive L. So L equal to 1, M must be negative 1, 0, positive 1. So again, I repeat, we don't look at the values of M. In M, we don't look at the values of M. If for L, we look at the value of L. L equal 1 means p orbital. But here M, we don't look at the values of M. We look at how many M will be produced. 1, 2, 3. We have 3 values of M, means 3 orientations for p orbital. For p orbital, 3 mutually perpendicular 90 degree of p orbitals. So this is PZ. We have orientation of PZ, PX, and PY. PZ, the lobe, 2 regions lobe, the lobe is on the z-axis. So that's why the name of this orbital orientation is PZ orbital. This is PX orbital because the dumbbell shape. Why is dumbbell? Because it is p orbital. So the dumbbell shape, 2 lobes on the x-axis. So that's why this is PX. PY, because 2 lobes on the y-axis. So for p orbital, we have 3 different orientations, which is PZ, PX, and PY. If L equal to 2, we know that L equal to 2d orbital. For d orbital, our M value is negative L, 0 until positive L. So our L is 2. M value, negative 2, negative 1, 0, positive 1, positive 2. We don't look at the value of M, we look at how many M. We can produce 5 values of M, means we have 5 orientations of d orbitals. Why d orbitals? Because L equal 2 means d orbital. So these are 5 orientation of d orbital. We have dxy, dxz, dyz, dx square y square, and dz square. For dxy, it is the lobes, it is cloverleaf. At xy, the cloverleaf must be in between the x and the y axis. So this is x-axis, this is y-axis. So 1 lobe in between, and this is x-axis, 1 and 1 y-axis. So 1 lobe in between, x-axis, y-axis, 1 lobe in between, x-axis, and y-axis, 1 lobe in between. So dxy means the cloverleaf is in between x and y axis. So that is dxy orientation of d orbital. For xz, the cloverleaf is in between x-axis and the z-axis. So this is x-axis line, z-axis line. The lobe must be in between x and z. So here in between xz, here in between x and z, this lobe in between x and z, and this lobe in between x and z. That's xz. Same goes to dyz. The lobe is in between y and z axis. This is between y and z. This lobe between y and z, and this lobe between y and z. Next, dx square y square means the lobe must be, the cloverleaf must be on the x-axis and on the y-axis. That's what square means. For dz square, two loops are on the z-axis. dz square is the only donut shape for d orbitals. The other four d orbitals are cloverleaf shaped. This is a video showing the orientation of s and p orbital. S orbital has sphere shape, so it only has one orientation. This is 1s, and bigger 2s. This is 2px orientation, 2py orientation, and 2pz orientation. For the following subshells, subshell 2p, 3s, 4dxy, give the values of the quantum numbers. So quantum numbers that we've learned so far is n, l, m, and the number of orbitals in each subshell. So for 2p, the n value is 2, p, l value equal to 1 because it's p, and if L is equal to 1, the m must be negative L until positive L. So our L is 1, m is negative 1, 0, positive 1. The total number of m is 3. The total m can be produced from L is 3. So p orbital has 3 orbitals. For 3s, n equal to 3, s means it is L equal to 0. So when L equal to 0, m equal to 0, s orbital only has one orbital because it only has one value of m. For 4dxy, n equal to 4, d is L equal to 2 means L equal to 2 means d, but it is specified, it is dxy. In D, we have 5 different orbitals: dxy, dyz, dxz, dx square, y square, and dz square. So there are 5 orbitals for D, but this is the 4dxy subshell, means only one value of m. N equal to 4, L equal to 2 because it's D, but it's specified dxy, so means one value of m only. You cannot write all of them because it's only dxy, not general D. If general D, you can write negative 2, negative 1, 0, positive 1, positive 2. But it is specified one type of d orbitals only, so you can only write one value of m. It's either negative 2, or negative 1, or 0, or positive 1, or positive 2. Like for this one, for A, it doesn't specify whether it is px, py, or pz. So you can write all of them. Negative 1, 0, positive 1. So it's negative 1, probably px, 0, probably py, positive 1, probably pz. It can be changed, or you want to say positive 1 is px, it's fine. 0 is pz, it's fine. Negative 1 is pz, it's fine, as long as these three has different orientation of p. The last one, electron spin quantum number S, represent the spinning motion of the electron in its own axis. So the electron, it spin on its own axis. It has two values, positive half and negative half, two possible motions of an electron, clockwise and anti-clockwise. Each orbital consists of two electrons with opposite spin. So one electron, it can be spinning clockwise or anti-clockwise. Clockwise positive half, anti-clockwise negative half, or you can say anti-clockwise positive half, negative half for clockwise, as long as they are different. And in one type of orbital, in one orientation, in one type of orbital, two electron maximum can be in that orbital. For example, in px, only two electron maximum can be in px. The maximum number of electrons in an orbital equal to 2. For example, in 3D subshell there are 5 orbitals, so total maximum number of electrons are 10. So this is 3D orbital diagram. So we have dxy, dyz, dxz, dx square y square, dz square. So in each orbital, the maximum number of electron can be occupied in each orbital is 2 electrons. In L equal to 0, n equal to 1, L equal to 0, m equal to 0 because our L is 0, m values depends on the value of L. Our subshell NL, so 1s, subshell 1s. S is the electron spin quantum number, positive half, negative half. So maximum number of electron in one subshell or 2 electrons. So 1 electron positive half, another 1 electron negative half. For n equal to 2, L can be 0, L can be 1. If L 0, M 0, 2s, positive half, negative half, 2 electron. And if L equal to 1, our M is negative 1, 0, positive 1. M values are negative L until positive L, so our L is 1. The value is negative 1, 0, positive 1. So we have 3 difference orientation. This is p orbital, L equal to 1, p orbital. So we have px, py, pz. This is 2p. So in each orbital, 1, 2, 3, in each orbital, maximum number of electron can be occupied 2 electrons. So that's why in total we have 6. 2, 2, 2. For n equal to 3, L equal to 2, the values of m are negative 2, negative 1, 0, positive 1, positive 2. So this is d orbital. D orbitals we have 5 different orientation: dxy, dyz, dxz, dx square y square, dz square. Each of these orbital maximum number of electrons are 2. So that's why we have 10 maximum number of electron in L equal to 2. Set of quantum numbers can be written in bracket n, L, m, s. All sets of quantum numbers for electron that occupy 2p, n equal to 2, L equal to 1, because p means L equal to 1. When our L is equal to 1, m values are negative 1, 0, positive 1. Only 2 values for electron spin, which is positive half and negative half. We have to write the set for 2p, all sets of quantum number. We start with 2, 1, n, L, m. Our m, you start with negative 1, positive half, and then 2, 1, still negative 1, negative half. And then carry on with 0, 2, 1, 0, positive half, negative half, and then 2, 1, 0, negative half, 2, 1, positive 1, positive half, 2, 1, positive 1, negative half. So for 2p, we have total of 6 sets of quantum number. Write 4 quantum numbers for an electron in 4s. 4 quantum number means we want n, L, m, s. For n electron means you need to write for 1 electron only in 4s, because we know 4s maximum number of electron can occupy 4s orbitals or 2 electron, but we only want the quantum numbers for n electron only, so we have 1 set only. This in p orbital, the maximum electrons can be occupied in p orbitals are 6 electrons. That's why we have 6 sets of quantum number, because maximum 6 electron. But in 4s, maximum 2 electrons only, but the question only asks for n electron, for 1 electron only. So write the 4 quantum numbers for 1 electron only. N equal to 4, L equal to 0 because S is 0, M equal to 0, and S equal to can be positive half or can be negative half. If you have to write the set of quantum number, you have to put 4, 0, 0, negative half, or 4, 0, 0, positive half. But you must write one set only because it's for one electron only. Don't write two sets, only one set. If you want to write both, make sure you put the word or, not n. N means for two electrons. Or means it can be this one or it can be this one, only one. What is the designation for the subshell with n equal to 5, L equal to 1? So we know our L equal to 1 means p orbital. And indicate the values of m for each of these orbitals. Our subshell, 5p. When L equal to 1, we know that m values are negative L until positive L. So negative 1, 0, positive 1.